Process scheduling is the activity of choosing which process should run on the CPU at any given time and for how long. The goal of process scheduling is to maximize the CPU utilization, which means keeping the CPU busy as much as possible. One way to achieve high CPU utilization is to use time sharing, which means switching the CPU among different processes quickly. This gives the illusion that multiple processes are running simultaneously on the CPU, even though only one process can run at a time. The process scheduler is the component of the operating system that performs this switching. The process scheduler uses various algorithms and criteria to decide which process should run next. The process scheduler also maintains several queue of processes that are in different states. A queue is a data structure that stores a collection of items in a specific order. The process scheduler uses this queue to organize and manage the processes in the system. The first queue is the job queue, which contains all the processes that exist in the system. A process is created when a program is executed, and when it terminates, when it finishes its execution, or when it is killed by another process or by the user. The second queue is the ready queue, which contains all the processes that are residing in main memory and are ready to run on the CPU. Main memory is the fast and volatile memory that stores the instruction and data of program while it is executing. A process can only run on the CPU if it is in the main memory. So the ready queue keeps track of all processes that are waiting for their turn to run on the CPU. The third type of queue is the device queue, which contains all the processes that are waiting for the input-output device. An I/O device is a hardware component that allows a process to communicate with external devices or users, such as a keyboard, a mouse, a printer, a disk, and etc. A process may need to perform an I/O operation during its execution, such as reading from a file or printing a document. When a process requests an I/O operation, it cannot run on the CPU until the operation is completed. The device queue keeps track of all the processes that are blocked by a I/O device. So in figure 3.5 in the textbook shows example of this queue and how they are related. Processes can move from one queue to another depending on their state and event that occur in the system. For example, when a new process is created, it enters the job queue. When there is enough memory space in the main memory, it moves from the job queue to the ready queue. And when the process scheduler select it to run on the CPU, it moves from ready queue to the CPU. When it requires an IO operation, it then move from the CPU to the device queue. When the IO operation is completed, it moves from the device queue back to the ready queue. When it finishes its execution or is killed, it then moves from either the CPU or device queue to termination. So a common way to represent process scheduling visually is using the queuing diagram, which show how processes flow among different queue and resources in the system. Figure 3.6 in the textbook show an example of queuing diagram for process scheduling. This slide shows the ready queue and various I/O device queue in a system with multiple processes. The ready queue is a list of processes that are waiting to be executed by the CPU. The I/O device queue are lists of processes that are waiting for a specific I/O device to become available, such as a disk or a printer. The figure illustrates how the process move between the ready queue and the I/O device queue. When a process is created, it is placed in the ready queue. When the CPU scheduler selects a process from the ready queue, it assigns the CPU to that process. The process then starts executing its instruction. During its execution, a process may request an I/O operation, such as reading from a file or printing document. In that case, the process is moved from the CPU to the corresponding I/O device queue. The process waits in the I/O device queue until the I/O operation is completed. When the I/O operation is completed, the process is moved back to the ready queue. Alternatively, a process may be interrupted by a timer or another event such as signal or an exception. In that case, the process is moved from the CPU to the ready queue. The process waits in the ready queue until the CPU scheduler select it again. The figure also shows that there may be multiple I/O devices queue for different types of devices. For example, there may be separate queue for disk, printer, keyboard, and etc. Each I/O device has its own I/O controller that manages the communication between the device and the processors. The I/O controller may also have its own scheduling algorithm to determine which process in the I/O device queue get access to the device. These sections explain the concept of scheduler in an operating system. Schedulers are responsible for deciding which processes get to use the CPU and for how long. There are two main types of scheduler, which is short-term and long-term. The short-term scheduler, also called the CPU scheduler, which select which process from the ready queue should be executed next and allocates a CPU to it. The ready queue is a list of processes that are waiting for the CPU. The short-term scheduler is invoked frequently, which is every few milliseconds, because processes may finish their CPU burst or get blocked by the I/O request. Therefore, the short-term scheduler must be fast and efficient. The other type is the long-term scheduler, or also called the job scheduler. So here, the long-term scheduler selects which processes should be brought into the ready queue from the pool of available processes. The pool of available processes is a set of processes that are not yet in the system but are ready to be executed. The long-term scheduler is invoked infrequently, which is every few seconds or minutes, because it does not need to react for every change in the system. Therefore, the long-term scheduler can be slow and complex. The long-term scheduler controls the degree of multi-programming in the system. Multi-programming is the ability of the operating system to run multiple processes concurrently on one or more CPU. The more processes are in the ready queue, the higher the degree of multi-programming. However, having too many processes in the ready queue can also cause problems such as increased overhead, contention, and starvation. Processes can be described as either I/O bound or CPU bound, depending on their behavior and resource requirement. An I/O bound process spends most time doing I/O than computation and has many short CPU bursts. An I/O bound process typically needs fast access to the I/O device and does not use much CPU time. A CPU bound process spends more time doing computation than I/O and has a few very long CPU bursts. A CPU bound process typically needs long periods of uninterrupted CPU time and does not use much I/O devices. The long-term scheduler strives for a good process mix in the system. A process mix is a combination of I/O bound and CPU bound processes that optimize the utilization of both CPU and I/O resources. A good process mix balances the load of the system and avoid wasting resources or creating bottlenecks. The process scheduler is responsible for deciding which process should run on the CPU at a given time. It has three layers, which are the long-term scheduler, the short-term scheduler, and the middle-level scheduler. The middle level scheduler is the third layer of the process scheduler. It is used in highly interactive environments, such as a graphical user interface or web server, where there are many processes competing for CPU time and memory. The middle level scheduler handles overloading, which means that there are more processes in memory than the system can handle efficiently. The middle level scheduler can remove some active processes from memory and store them on disk. This reduces the degree of multiprogramming, which is the number of processes that are in memory at the same time. By doing this, the middle level scheduler can improve the performance of the system and make the processes complete faster. The middle level scheduler is not needed in a single user environment where there is only one user and one job running on the system. In this case, there is no distinction between job and process scheduling because a job is a collection of one or more processes that belong to a user. The single user environment has only one job active at a time and it receives all the system resources for its duration. This slide is about multitasking in mobile system. Multitasking is the ability of an operating system to run more than one process at a time. One way to implement multitasking is to allow only one process to run in the foreground while other processes are suspended in the background. This was the case for some early version of iOS, the operating system for iPhone and iPad. However, this approach has some drawbacks, such as poor responsiveness and limited functionality for background processes. Starting with iOS 4, Apple introduced a more flexible multitasking model. In this model, there are still a single foreground process that interact with the user interface, but there are also multiple background processes that can perform certain tasks in memory. However, these background processes have some limits on what they can do and how they can run. For example, they can only execute a short task, receive notification of event, or perform specific long-running tasks like audio playback. These limits are imposed to conserve battery life and memory resources. Another way to implement multitasking is to allow both foreground and background processes to run without many restrictions. This is the case for Android, where the operating system for smartphone and tablet that use Google software. In Android, a background processor can use service to perform tasks that do not require user interaction. A service is a component of an application that runs in the background and has low memory usage. A service can keep running even if the background process that started it is suspended by the operating system. This allows for more functionality and flexibility for background processes, but it also consumes more battery power and memory resources. A context switch is the process of saving and restoring the state of a process when the CPU switches from the executing one process to another. The state of process includes all the information that the CPU needs to resume the execution of the process, such as the program counter, the register, the stack pointer, and so on. The state of the process is stored in data structure called the process control block or PCB, which is maintained by the operating system. A context switch is necessary because the CPU can only execute one process at a time, but there may be many processes that are ready to run. The operating system uses a scheduling algorithm to decide which process to run next and then perform a context switch to switch from the current process to the selected process. A context switch is also triggered by events such as interrupt, system call, or signals which may cause the current process to be blocked or preempted. A context switch is pure overhead for the system because it does not perform any useful work for the processors. Here, it only assumes CPU time and memory resources. Therefore, the context switch time should be minimized as much as possible. The context switch time depends on several factors, such as the complexity of the operating system and the PCB and the hardware that supports for context switching. For example, some hardware provides multiple sets of registers per CPU, which allow multiple contexts to be loaded at once and reduce the number of memory accesses required for a context switch. A CPU switch from one process to another is called a context switch. A context switch involves saving the state of current process and loading the state of the next process. The state of process includes all the information that the CPU needs to execute the process, such as the program counter, the register, the memory map, and the open file. A context switch can happen for various reasons, such as when a process finishes its time slice, when a process blocks on I/O, when a process is preempted by a higher priority process, or when an interrupt occurs. A context switch is an overhead for the CPU because it takes time to save and load the process state. Therefore, the operating system tries to minimize the number of context switches. The figure 3.4 shows an example of a context switch between two processes, which is P0 and P1. The CPU is executing P0 until it encounters an I/O request. The CPU then saves the state of P0 in its PCB or process control block and loads the state of P1 from its PCB. The CPU then executes P1 until it finishes its time slice. The CPU then saves the state of P1 in its PCB and loads the state of P1 from its PCB. The CPU then resumes the execution of P0 from where it left off. This slide explains the different situation when a process can be switched by the operating system. A process is a program that is executing on the CPU. The operating system can switch between different processes to share the CPU resources and improve the system performance. One situation is when a clock interrupts occur. This means that the process has executed for the maximum allowable time slice, which is a fixed amount of time assigned by the operating system. The operating system can then switch to another process that is ready to run. Another situation is when I/O interrupts occur. This means that a process has requested some input or output operation, such as reading from a disk or printing to a printer. The operating system can then suspend the process until the I/O operation is completed and switch to another process that does not need I/O. A third situation is when a memory fault occurs. This means that the process has tried to access a memory address that is not in the main memory, but in the virtual memory. Virtual memory is a technique that allows the operating system to use this space as an extension of the main memory. The operating system can then bring the required page of the virtual memory into the main memory and switch to another process while waiting for the disk operation. A fourth situation is when a traps occur. This means that an error has occurred during the execution of the process, such as dividing by zero or accessing an invalid memory address. The operating system can then terminate the process and move it to the exit state and switch to another process that is not in error. A fifth situation is when a supervisor call occurs. Here, this means that the process has requested some service from the operating system, such as opening a file or creating a new process. The operating system can then perform the service for the process and switch to another process while waiting for the service to be completed.